Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of websites that are either malicious or benign. And we have a bunch of data about each website, and at the end of the columns we have this type, which is 1 for malicious and 0 for benign. So we're going to do a binary classification on the type of website given all this data. So let's hop into the notebook. We're going to use a logistic regression model to make our predictions. I am importing NumPy and pandas for working with the data, then pyplot from matplotlib, and seaborn for visualization. Then for pre-processing, we're going to use the train test split function and standard scaler from sklearn. And like I said, logistic regression model from sklearn as well. And we're going to import the confusion matrix and classification report from sklearn.metrics in order to analyze the results of our model. Let's go ahead and import that. And let's load in the data using pandas.readcsv. So over here, we can go up and grab the dataset.csv file, paste that in, and take a look. Alright, we have 21 columns, which just goes over the maximum number of columns that pandas allows us to see at once. So let's go in and change that with pandas.setOption max columns none. That will just allow us to refresh this, and then we can see all 21. Alright, so you can see we have at least some missing values that have been encoded as none, but it's also maybe important to keep this as a possible category, because this is the country reported from whois. We actually have some real missing values here, and at the end it looks like all these are numerical. We can actually go into the dataset and see a description of all the features, and it actually tells us which are categorical. So there are actually 4 categorical variables here, which would be the character set, the server, the whois country, and the whois state pro, which is the states that they got a server response from. Alright, so let us take a little closer look with data.info. And here we can see that there's actually one missing value here, and a few here, and one here. So not too bad on the missing values. We also have some object columns that we're going to have to encode, and I notice that we also have some date-time columns that we're going to have. We can use pandas.toDateTime to extract features from these columns. So let's start. What I'm going to do is create some helper functions, one of which will be pre-process inputs, which is all of our pre-processing will happen in here. This is going to take in a data frame, and we'll start by creating a copy of that data frame. And at the end, after we do all of our pre-processing, we'll return the data frame again. So currently, if we have data at the top, and at the bottom, let's call it x. X will be our pre-processed data. Then we call pre-process inputs and pass in our original data, and we take a look at x. We then have a pre-processed version of it. Now currently they're identical because we just made a copy, but now we can perform any changes to this copy and see the results down here. So the first thing I'd like to do is actually drop this URL column, and the reason for that is this isn't actually information about the URL. It's only a unique identifier. I believe the M stands for malignant and B stands for benign. So it's basically just an ID column, which is not going to provide any useful information in predicting the malignant or benign. In fact, it may actually, well, if we used, for example, the first letter of this, we would be cheating, because that's also the label is sort of built into this ID. So let's go ahead and drop URL from axis 1, which is the column axis. I'll just comment it, drop URL column. Alright, now if we run this and take a look at x, you can see the URL column is gone. And next, what I'd like to do, I think I just want to go ahead and straight away deal with the datetime columns. So we have 2 datetime features, and currently they're encoded as strings. Luckily, pandas comes with a very useful function called toDateTime that allows us to take in one of these strings, or a series of these strings, or a data frame of these strings, and convert it into a datetime object, which we can then use attributes like year to get the year, month to get the month, day to get the day, hour to get the hour, and so on. So we can actually extract all these different features out of the original datetime column using this pandas function. So we can do over here, extract datetime features. The first thing I'd like to do is actually convert the columns to datetime features. So for column in, and there's only two here, but I'm going to take this and put them in a list so that we can do them, apply the same processing to both columns. So it's who is reg date, I guess registration date, and who is updated date. So for each column, I'd like to set that column equal to pandas.toDateTime of that column. Now if we run this, we're actually getting an error. And that's because datetime doesn't know what to do with none. So in the toDateTime function, when it encounters a value that it can't interpret as a datetime, there are three things we can do. One, by default, we can raise an error. So that's exactly what this is doing. Two, we can ignore the error, which will actually perform it and leave all the nuns the way they are. Or we can coerce, which means let's turn it into NAT, which stands for not a time. And so this actually counts as a missing value. And what's nice about this is when we go ahead and extract the features, the year, month, day, etc., these will just be ignored. Whereas if we do ignore them, if we keep it on ignore and keep those nuns in there, when we go ahead and extract the features, we're going to have to deal with this special case. So I think by using coerce here, we're actually doing ourselves a favor. And now that they're in datetime format, and anything that couldn't be converted to datetime is now NAT, we can go ahead and get the all the information that we need from it. So let's create a year column from the who is reg date. So we want to extract this value from each example and put it in its own column. So to do that, all we have to do is create a new column here. Let's call it reg year. And that's going to take the original who is reg date column and apply a lambda function to it that takes in some x, which in this case will be a datetime, an actual datetime object, and it will return x.year. So for each x, we're going to change it to x.year only, and we're going to store that in its own column. So if we run this, you can see at the end here we have the year, and it has extracted all the years, and in addition it has also filled in not a number values for the not a time entries. So the benefit of using this coerce method is that we can actually just ignore it and just continue to extract the features regardless. Alright, so let's do the same thing for month, day. I guess we could do hour and minute also, but I do not see any value in using seconds. I mean, you can. We don't have too many features here. I think when we're done with this, we'll end up with like a few hundred features. So including that seconds, I mean, it's really going to be negligible if you get anything out of it. But especially year, month, day are extremely useful, and I assume hours also. I guess we can include minute as well, but it's really not essential. So here's month, here's day, here's hour, and here's minute. And I'm getting those all from the same column, right? But I want to store them in their own respective columns. So this we'll call reg month, this we'll call reg day, this we'll call reg hour, and this will be reg minute. And it's as simple as that. We run this now. You can see we have all these new values, where all the values here have been extracted from the original datetime values. So let's do the same thing for the updated date column. So all that means, we'll just grab this, copy it over, and the only thing that changes here is the names of the columns. So these are all going to be, how do we call it, UPD year for updated. And then this has to be who is updated date. So all of these, we just grab them all like this, and we're going to paste in who is updated date. So this will give us all the 5 columns from this column and all the 5 columns from this column. And then when we're done, we really don't need those original columns anymore, so we can drop those. So we're going to drop these guys here, and we're dropping from axis 1, which is the column axis. Alright, now let's take a look. We no longer have the date-time columns. At the end, we have all the information we need encoded in their own ordinal features. So, I guess now we can one-hot encode. So let's take a look at some of the values that are stored inside inside each column. I'm not really concerned with the numerical values, but the categorical values do interest me. I want to know, specifically how many categorical values or unique, distinct categorical values we have in each column. So we can do that by creating a dictionary that's going to map a column name to the length of unique values in the column, and that's going to be for every column in x.selectDtypes object.columns. So let's look at x.selectDtypes object. If we just run that little bit, you can see it just selects all the columns that have a data type of object, or in this case string. So if we get the dot columns of that, it will return just the column names that have objects as the data type. So if we iterate through these column names, we can then display a pair containing the column name and the number of unique values in that column for every object column in the dataset. And here it is. So these are our categorical columns. These are the ones we're going to one-hot encode. It was stated over here as well that these are the categorical features. And you can see that these are very reasonable numbers for one-hot encoding. So one-hot encoding uses, we can use the pandas.getDummies function to take one of these columns, let's say character set, and you can see now that each unique value in the original character set column gets its own column and a 1 or a 0 for each one, depending on what the original value for an example was. So for example 0 and example 1, if we look up, that's ISO 8859-1 and UTF-8 respectively. And so over here we have a 1 in the ISO 8859-1 column, and we have a 1 here in the UTF-8 column. Now I do notice there are actually some overlaps here. It looks like maybe this wasn't encoded. You see, this is exactly the same as that, and I'm not I'm not sure about what all of these mean. So I don't know if this is actually the same as this. This has a -1 at the end. This doesn't, and I'm not sure about the difference. But I can be almost sure that these are the same. So what I'd like to do is actually change them all to be lowercase before we perform the one-hot encoding. And I guess we can just do that for all of them. Yeah, so let's one-hot encode categorical features. And for this, we're going to use a function that we create called one-hot encode. It's going to take in a data frame and a column dictionary. And we'll start by creating a copy of our data frame. And then we will iterate through every column prefix pair in column dict.items. So let me explain what this is. So over here, when we are getting these dummy columns, we can include a prefix. Let's say char for character. And that will just add a little indicator at the beginning of each column name so that we know where the dummy columns originally came from. And so what I'm going to do is I'm going to pass into this one-hot encode function a dictionary that maps a column name to a prefix. So we can pass in those two values at once, sort of. So if we call .items on a dictionary, we'll return the key value pairs as tuples. which we can then iterate through 2 at a time like this. I realize we could probably just pass this in as a list of tuples as well, which might make things easier, but it doesn't really matter. Alright, so let's create a dummies data frame. So this, we're going to use the pandas.getDummies function, and we're going to do it for every column with the prefix that comes with it. And then we're going to basically take these dummy columns and put them on the end of our data frame. So we can do that with pandas.concat, pass in the data frame and the dummies, and we want to specify axis 1, so that means concatenate them side by side. And that's going to be our new DF. Then once we've concatenated them, we can drop the original column from which we created the dummies, because it's no longer of use to us. And then we'll return DF. So this will one-hot encode the whole data frame with as many categorical features as we choose to pass in. So like I said, before I encode them, I'd like to set all of the values to lowercase so that we can just eliminate anything like this. So let's say, okay, df, actually for column in, and I want to specify all the categorical columns now, which are these ones. And we can just go in and remove the dictionary entries. So now it's a list of the column names. For each one, let's apply a lambda function. That's going to just send x to x.lower. And I think that should do it. After that, we're going to one-hot encode. And for this, we pass in the data frame and our column dict. And the column dict, again, is going to match a column name to a prefix. So here are our column names. First we'll have charset, and that can get mapped to, how about we'll use ch. Then server, and we can map that to sv. Then who is country, and we can map that to wc. And who is state pro, we'll map that to ws. And so this will do it for us, right, because of the function we made. So run this, we take a look. Oh no, we have a float in there. So there may be a missing value in here, which is encoded as a float. So maybe we just won't do this. I don't know. It's really not essential. I'm just trying to avoid overlap. But okay, well actually, easy workaround. We can set it x equal to x.lower if string of x is not nan. This is basically saying if we're not dealing with a missing value, let's set it to its lowercase version. Otherwise, we'll leave it the way it is. And that should do it. Alright, so here are all of our one-hot columns, and they have been lowercased. Okay, so we ended up with about 475 columns. And I guess now we can fill those missing values. So we have some missing values, and you'll note that the dataset is fully numeric now. So any missing values we have can just be filled in with the column means. You can really use any statistic about the columns that you like, but the mean is probably the most common and easiest. You could also use mode or median or whatever you like. Fill missing values. What I'm going to do is save the column names from all the missing value columns. By that I mean any column that has more than one or more missing values. We'll save it in this list. So we can get that with x.isNA. This will check true or false for every entry whether or not there's a missing value in that location. So here you can see we have some missing values, and that corresponds to these here. If we sum over the rows with .sum, sorry, like this, then we'll get the number of missing values in each column. And basically, we can ask, is it greater than 0? And it will return false or true, depending on the condition, if the condition is met within each column. And we can actually use this true-false Boolean series as an indexer in our data frame columns. So x.columns, using that as an indexer, will give us all of the columns where that condition is true. So these are all the column names that have more than one missing value. So let's, over here, we'll call it missing value columns. And that will just be this. And then all we have to do is say for column in missing value columns, df subcolumn equals df subcolumn dot fill na. This function from pandas allows us to fill all the missing values with a given value, and the value we're going to give it is the mean, df subcolumn dot mean. And this won't throw any errors because we know all of the columns are numeric, so the mean is calculatable. Alright, let's run this and see what we get. Alright, so it looks the same. You can see those missing values have been filled in. And if we look at the means, if we look at the missing values again, this time I want to sum over the rows to get the number in each column, and then again over the columns to get the total number in the data frame. So you can see we have no more missing values in there. So we've dealt with missing values. Now we're going to split and scale the data. So split df into x and y. So y is going to be what we're trying to predict, which in this case is the, where is it? Type column. This guy. This is whether the website is malignant or benign. So y will be df subtype, and let's just make a copy of it. And then x will be everything except the type column. So df.drop type. And we're dropping from axis 1. And let's also make a copy. Alright, now that we've split vertically, we've removed this column from the data frame. Let's actually return x and y. And now you can see if we get those values, x referenced for assignment. Oh yeah, this should be df, sorry, when we fill the missing values. Okay. Here we go. Alright. So x doesn't have the class column anymore, but we can get that from y. Now it's been split off, and this is sort of like the answers to our predictions, and we're going to try to make predictions based on x. So now let's also do a horizontal split, so a train test split. This will save some amount of the data for testing and evaluating the model, and we'll train the model on the rest of the data. So for this, we're going to use the train test split function from sklearn, pass in x and y, and specify a train size. 70% is a good standard. Then the random state, we include this because this function also shuffles the data for us, so we don't have to do it ourselves. And the random state will ensure that the shuffle is always made in the same way. And that will return 4 new values: x train, x test, y train, and y test. So first we're splitting into y and x, and then we're splitting y and x into these 4. And then let's actually return those instead of just x and y down here. And get them over here. And take a look. So x train, it's the same as x, but it's only on 70% of the data. And a y train is the answers to all the train set examples. Alright, so let's scale. So we're going to use a standard scaler. So scale x with a standard scaler. And a standard scaler is just going to give each column a mean of 0 and a variance of 1. A lot of models prefer that all the columns take on a similar range of values. So by scaling the data, we can increase the performance of our model. So the scalar will be standard scalar, and we're going to fit the scalar to the train set. Sorry, scalar.fit on xtrain. And the reason for just fitting it on the train set and not all the data is because you want to treat, you want to sort of approach the task as if you have never seen the test data and that you don't have access to the test data. Because in production, if you're really making a model that's going to work in the wild, then you would not have access to the test data, and the test data can come in at any time. So the train data is all you have, so we're going to fit the scalar to the train data. And then we're going to transform the train data using scalar.transform on xtrain. So this will actually, after it's been fit, we will then apply the shift and scale to each column, and we'll do that for xtrain and also for xtest. So I'll note that this function returns a NumPy array, so I'd like to turn it back into a data frame when we're done, and keep the column names as x.column names, x.columns. So let's do the same thing down here and return that. And now we can see that xtrain does have mean of 0 and variance 1 in each column. You can actually check that to be double sure with the mean. So you can see that all the means are extremely close to 0 and variances are extremely close to 1. So the scalar has done its job. And we did not scale y. We want to keep y as just a 0 or a 1 depending on the example. Now I would like to point out an issue with this. Because we only fit the scalar to the train set, if we scroll through here, you'll see we have some rows, some columns with all zeros. And this is an indication that the column had only one value in it before we scaled. Because whatever that value may be, it's just going to be sent to 0 and no scale is needed. There's only one value in there. And that can be the case with one-hot columns. Now, when you one-hot encode, there's always going to be two values for a given column, because there had to be at least one of those examples with this value. But that value may have ended up in the test set, and we no longer have access to the test set. So essentially, with this particular train test split, the only occurrence of this example, of this unique value, ended up in the test set. And so that's why we're getting 0 here, because we only had zeros in the original. So if I do not scale, let's pretend we don't scale, and we just look at this, and we go over, you can see some of these are going to have all zeros. I'm not sure which they are, but if we actually look at the number of unique values, so I'm going to grab this from before when we checked the number of unique values in each column. I'm going to do the same thing, but this time for xtrain. And I'm not going to worry about the object columns. I'm only going to look at all columns. And you can see down here, we do indeed have some one-hot columns that have only one value. That means that they're all zeros, because the only one that it had is now in the test set. So the only thing we can do in this case is actually drop these columns. Because if you look at the test set is actually also, how do I say? It's like, essentially, we're using more data in the test set than we had available to us at time of training, which is not right. Additionally, yeah, okay. So we're just going to drop all of the columns that have one value. And so to do that, what we can do is take xtrain, and we're going to ask the question, is the number of unique values, so the length of the unique values, equal to 1? oh sorry, for a given column. For a given column, is the length of unique values in that column equal to 1? And we're going to do that for every column in x.columns, xtrain.columns. And so we'll have a true or a false, and anytime we see a true, that means there's only one value in that column. And like I did before, we can then use this Boolean list as an indexer in xtrain.columns. Okay, maybe not. We actually should, instead, if this isn't working, what we can do is use the .loc function, target all rows, and just these columns. Wait, what is this? Maybe I made a mistake here. Hold on. This seems to work. Oh, okay, yeah. Okay, so xtrain.columns, but I have to use an additional bracket there. Alright, and this is the name of all the columns that have only one value. So these are the columns. So what I'm going to go ahead and do is up here, we're going to remove feature columns that were reduced to single value columns during the train test split. And so this is the list of all of our single value columns. So I'll call that single value columns. And then we're going to drop them. So we drop them from both the train set and the test set. Xtrain equals xtrain.drop single value columns axis 1. And we'll do the same thing for the test set. Okay. And now we should not have to worry about that at all. If we go back and re-enable the scaling, and we take a look over here, you can see there are no more columns with all zeros in them. So everything has been cleaned up, and we now have like proper data to use to make predictions on. So I think that's everything we need to do in terms of pre-processing. So let's clean this up a little. Just remove this and this stuff. Alright. So we have helper functions. I'm going to remove this as well. These are our helper functions, and then down here the actual pre-processing is happening. Now we're going to train. So training. We'll just create a model, which will be a logistic regression. And we're going to fit the model to the train set. Xtrain, Ytrain. Alright, it's fit. And now I'd like to create a function called evaluate model. That's going to take in a model, a test set, and return the results. So I'll put that down here while we do it. Evaluate model. That's going to take in a model, some x test, and some y test. And we can start by getting the accuracy value. So model.score will give us that. We pass in x test and y test. And then we can print it out. Test accuracy. And why don't we format it to 2 decimal places, give it a %sign, and then format in the model accuracy times 100 so we can see it as a %. So now if I run this function, evaluate model, passing in model, x test, and y test, it just returns the accuracy. And you can see that's fairly good, or so we believe. Accuracy can be a very misleading metric. And if we look at the Ytrain, so this is the distribution of, actually let's look at Y-test since we're looking at the test accuracy here. So Y-test is just zeros and ones, one being if it's malignant or not. So if we get the value counts for this, we can see how many of each we have. And you can see we have substantially fewer malignant websites than we do benign, which makes sense because uh, that trend exists pretty much with any sort of fraud detection or uh, malignancy detection. You're going to get some sort of class imbalance like this. And so if we look at that percentage, 466 plus 69, and we see what percentage of it is malignant. So 69 over that value. You see only 12% is malignant. And if we look at the other side, 466 over that value, 87% of the data is benign. So actually, it looks like maybe our model is doing better than expected. If we only guessed benign for every example, we get an accuracy of 87%. But you can see that our accuracy goes quite above that. So we can get a better idea of how the model is behaving by getting a confusion matrix. And for this, we're going to need a set of true values and predicted values. So the true values, y true, is just going to come from ytest, but I'll turn it into a NumPy array. And our predicted values, ypred, will just come from model.predict xtest. These will both be NumPy arrays, which we think can compare together in the confusion matrix function from sklearn.metrics. We pass in ytrue and ypred, and why don't we store that in CM? So we'll print out CM, so you can see. And we want to run this evaluate model. So here's the confusion matrix. And you can see we're doing quite well. These are true positives, well, true negatives, true positives, if you consider the malignant class as the positive class. So we don't have very many false positives, and we don't have very many false negatives. So the only thing is this looks a little boring to look at, and it's not very informative. So I'd like to go in and create a plot, a heat map that's going to make it look a little nicer. So let's create a new matplotlib figure. The figure size, this could be 8 by 8, some square. And then we'll use a seaborne heat map to plot CM, our confusion matrix. We'll turn on annotations. We'll set the minimum value to be displayed as 0. And we'll also include this format equals G, because by default we'll see the values, the counts like this in scientific notation. So by using G, we'll get just the integer values. Then we'll also pass in a color map. So blues looks nice for confusion matrices. And then a color bar. We actually want to turn off the color bar. So C bar equals false. And if we show, so instead of printing it, we'll just show and then run this. There it is. Looks a lot nicer, but it's not labeled. So let's go in and label it. The x-axis represents our predicted values, and our y-axis represents the actual values. Then we'll give it a title as well, confusion matrix. So almost done, but I do not like these little zeros and ones. So what I'll do is go in and actually set the tick marks, plot.xticks. So we have to pass in a list of locations for where to put the tick marks. By default, if we use NumPy a range with 2 values and pass in the label names, so 0 is benign and 1 is malignant. So if we run this and take a look, you can see it's doing it, but the problem is the tick marks are on the corner and in the middle. So we can fix that by going and adding 0.5 to the A range. And now you can see they show up in the right places. So let's do the same thing for the Y ticks. So Y ticks. And then take a look. And here we go. So this is a nice confusion matrix. We get a good sense of what's going on here. And you can see that we're actually doing pretty well, right? We don't have too many false positives. We don't have too many false negatives. So even though there's a class imbalance, the model's doing quite well. What we can do further to give us a little bit more information is get a classification report. That comes from sklearn.metrics as well, and it also takes in a yTrue and a ypred, and we also just want to specify the target names, which will be this guy right here. So after we show the heat map, we can print out the classification report. I will backslash and put some hyphens to make it look nice, and then CLR comes after that. Alright, I'm missing 2 hyphens. Not really important, but there we go. Alright, and now we can see some stats about the confusion matrix. So currently, if we're looking at the benign class here, our true positives are significantly high. So we have a precision of 0.96, which means out of all the ones we predicted benign, which are these 2 values here, 96% of them are correct. So we got 17 wrong benign predictions. That would be a false negative if we consider Malignant as the positive class. Then our recall here is 0.98, and that's because that's saying out of all of the actual benign values, these 2 values, we have 98% of them correct. And so it seems like on all fronts the benign class is doing very well. We have a F1 score, which is like a combination of precision and recall. It's very high, 0.97. Then Malignant, we're actually doing quite well, but it's not as good. 0.85, 0.75, and this is because for the precision, that means out of all of our predicted malignants, we have 85% of them correct. And for recall, out of all of the actual malignants, we have 75% of them correct. So the F1 score shows the sort of balance between them. So how can we improve this? Now, I tried using various oversampling, undersampling methods, and they all seemed to really tank the performance of the model, but there was one thing I found that seemed to work, which is class weighting. So how do I go into this? I guess let's just open up Desmos. 1 second. I'll show you something pretty cool. So binary cross entropy is a very interesting loss function. I might make a video on this specifically in the future. But so for a regression task, like linear regression, we usually use the mean squared error. Squared error will look like this, where if 0 is the actual value, then the farther away we get from 0, the higher our loss goes. We could also use absolute error, which would look like this, where the farther away we get from 0, the higher our loss goes, but all at a linear rate instead of a quadratic. So this kind of loss isn't really going to help us with a logistic regression task or a binary classification task, because we're not really so concerned about how far away we are from sorry, the values only take 0 or 1. So this isn't a measure of how far away we are from 0 or 1. I mean, this would work okay if we were if our true value is 0, we could sort of use this to gauge how far away we are. But there's a cap. This is as high as our loss can go because we can't go past 1. Our highest prediction could be 1. So a workaround for this is to use a very nice loss function called log loss, or cross entropy loss. So that looks like this. If we take the natural log of x, I'm sure you're familiar with this graph. It's just a logarithmic curve. And if we wanted to use this as a loss function, it's not very useful because there's no values in the positive range here. But if we flip it over the x-axis, it then suddenly becomes a useful loss function. Where here, if our true value is 1, then as we get closer to the true value, our loss goes to 0. Where we have a 0 loss if we're actually hitting it right away. And the farther away we are from 1, remember we can only go to 0, we can't go past 0, the higher our loss gets. And actually, there's no limit to this. We'll just keep going the closer and closer we get to 0. So this is a very nice loss function for binary classification. However, this only applies when our true y value is 1. So how can we modify this to model the situation where our y value is 0? So we can take this, looking at the blue one now, and we can flip it over the y-axis by giving a negative x, and then shift it over by 1, so a plus 1 here, to get the y equals 0 case. So when our true value is 0, we now have a nice loss function to model that. If I turn off that, you can see the closer we are to 0, the closer we approach 0, and actually at 0 we have a 0 loss, which means we're correct. And the farther away we get, the higher our loss goes. So these two functions model the two cases in a binary classification problem. And so this is called cross-entropy loss. And it's basically a combination of these two. And the way we do that is by taking our yt. So let's call yt, this will be our whether it's true or false. So yt, let's say L of x, so loss. Yt can only be either 0 or 1. So it can be 0 or 1. This is the true value of the example. And so we want to use this in the loss function. So what we can do, note that 1 minus yt is 0. So it's actually the opposite. If yt is 0, 1 minus yt is 1, and if yt is 1, 1 minus yt is 0. So we can use this to sort of switch back and forth between these two red and blue functions here. So I'll do that by multiplying yt, which I'll do it up here, multiplying yt by the first one, and then adding 1 minus yt times the second one. And now you'll see we have this function that's a combination of the first two, but it has these factors at the beginning. And it switches back and forth depending on the true value of yt. So this is cross-entropy loss, and it's used in almost every, this is the most common loss function that's used in classification problems. And the reason I bring this up is because I want to introduce the idea of weighted loss. So if we pass in some weights here, let's say WP for the positive class, and this should be the negative class, WN and WP. So these can take values from 0 to anything, and these are essentially ways to weight the loss for different classes. So currently they're both treated the same, with multiplied by 1. But let's say we want to penalize misclassification in the positive class only. So when y equals 1, we have, sorry, did I make a mistake? Right, yeah, this should be the positive one, and this should be the negative one. Okay. So when y equals 1, that means this term goes to 0, and so this whole thing disappears, and we're just dealing with this first part. And so we look at WP. And WP is basically, it's saying the higher this goes, the more we'll penalize bad results. So we can actually bring it down, or we can bring it up. It shouldn't actually be exactly 0. It could be like a really small value. But eventually, you can see, so we can bring this all the way up and leave the other one the same. And now you can see this is just as it was. But now this one is extremely steep. As soon as we get away from 1, we're going up really high. Whereas this guy, we sort of more of a gradual one. And if we bring the weight down on this, you can see we're much more forgiving for misclassifications on the negative class than we are if we're misclassifying on the positive class. And so these weights can allow us to sort of give the model a feeling that one of the classes is more important to get right than the others, since this loss function is the one being minimized. Alright, so that's what we're doing here. In the creation of our logistic regression model, we're going to pass in an argument called a class weight. It's a dictionary that's going to map 0 to a certain weight and 1 to a certain weight. So here's our negative class, the benign class, and here's our positive class. So there's a lot of different ways to do this. You can actually pass in balanced like this to automatically balance the weights based on the distribution of the classes. But you'll note if we do this, if we train it with a class weight of balanced, then originally we had, let's see, an F1 score of 0.97 in the 0 class, and an F1 score of 0.8 in the positive class. If we run this now, you can see our positive class actually went down. So the balanced weights did not work out. And it actually made it worse, right? Both the F1 scores in both classes went down. So let's see what does work. So instead of using this balanced, let's adjust them directly. If we have them as 1, that's the same as using no weight. So it would make sense to penalize misclassifications of malignant, like twice as hard maybe. But if we run that, you can see our score actually did go down as well. This 0.8 went down to a 0.78. And strangely, I really am not sure why this is. What actually ends up working here is lowering the class weight of the malignant class down to a very low amount, 0.25 maybe. And this actually really improves the model. Our F1 score went up to 0.98, and our down here it went up to 0.83. So, and you can see we have many fewer false positives here. And I found that lowering it even down to like 0.15 presents very nice results. We now only have 2 here. But it seems like the lower we go, we get a few more false negatives at the expense of false positives. So it's a bit of a trade-off. If you do like 0.2, you can see it's a nice balance between that. We now have 3 here and 19 here. So, but it definitely seems like lowering the weight of the positive class is making a significant improvement, or at least some improvement. Alright, and I guess that will conclude today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.